Okay, should be working. Okay, let's get started. So let's get back to our Fourier transform. So I guess first there is any question from last time? Okay, not then yeah, let's have a quick review of the Fourier transform. So as we said, we deal with Fourier series in chapter 3. Those in chapter 3 Fourier series we want to write. Maybe I should go to a different slide. So the Fourier series we want to write. We want to write some periodic function or any periodic function in terms of complex exponentials. And we know the harmonic related complex exponentials all have the same period. And we found out that you can actually write any periodic, well, not any, but most of the periodic functions in terms of the harmonic related complex exponentials. But in this chapter, we want to write any function in complex exponentials because we found out that if we write a signal in complex exponentials, then it's very easy to see how they go through LTI system. So we want to extend the Fourier series to Fourier transform, which is writing any function in terms of complex exponentials. And we do this by taking some limits. So we think about, we take any function and we repeat itself, so it becomes a periodic function. Then we push the period, repeating period t to infinity. So we think if we have a periodic function, but we have the period go to infinity, then it will look like a periodic function again. Okay? And we found out that what happened is, so first there is something very interesting. So there will be some AK, and well, there will be AK, that's the Fourier coefficients for those intermediate periodic functions. And but we found out that as we pick t larger and larger, the AK kind of follow the same trend. So there is an enveloping function here for those AK. And this enveloping function, so this TAK, actually doesn't change with your choice of big T. And so for example, this is the envelope function for the square wave. It's the sine over sine function. And what happens is when you pick the T larger and larger, you will have different AK, but AK will be actually like samples on this function. So you are taking discrete point on these functions, those will be your AK. So for example, it will be AK1, AK2, etc. And so what happens when you change T? When you change T, the big T get larger and larger, your sampling point will be more and more dense. So your sample, so this distance here is omega, and or more like omega naught. So the sample point here are at k omega naught, and omega naught will be 2 pi over t. And so you think as t goes to infinity, this sample is larger and larger, and you are basically getting information on all those enveloping functions. And so that's kind of how our argument goes. So we just so we think if we are taking all information, so how about we just take the this envelope function rather than the amount t as our Fourier transform of the signal or the spectrum of the signal. So it will tell you all the AK. And actually then we have some a little hand-wavy argument to say that. So if we take this, if we take this as the Fourier transform or spectra of our signal, then there are nice properties that so you can do the back and forth transformation just like in Fourier series because it has all the information on AK. So you can get so this big X function will be kind of like in the analysis relation, so this will be x of t times e to the minus j omega t and the integral. So you can calculate this big X envelope, and we argue that you can also get X back from the big X because because you can take a limit of your Fourier series synthesis equation. So as big T goes to infinity, your Fourier series where you sum over all those different k will be converge to like doing an integral on this big X will also times e to the j omega t. Okay. Because it's like you are summing the area of the triangle on area of those rectangles that's related to this big X times e to the j omega t curve, and as k go to infinity, not as k go to infinity, then as big T go to infinity, then those triangle gets thinner and thinner, and it's like you are just calculating the area under this curve. And anyway, so there are lots of arguments we make, and in the end we convince ourselves that we have this pair of Fourier transform formula. And so it's a bit more confusing. So this equation, which corresponds to the analysis equation in the Fourier series, is called the Fourier transform. So you transform from x of t to big X of j omega. So it's changed something from time domain to this omega frequency domain. And we believe that also you can transform back from x of j omega to x of t. So this is called the inverse Fourier transform equation. And x of t is equal to this integral of big X over j omega times e to the j omega t. But now there is something a little weird, different from the Fourier series equation we had. That is, we have this extra 1 to a 2 pi here. And so this is something actually a little annoying because this depends on our convention. This 1 over 2 pi is just because how we pick all the constants around. So we'll see very soon that there are different conventions where you put this 1 over 2 pi to different places. You can see that these two equations looks very similar. Big X is x of t times the convex exponential integral, and the x of t is the big X times another convex exponential integral. You need to be a little careful. So here you are integrating over dt, and here you are also integrating over d omega. And you need to remember big X is a function of omega, and small x is a function of t. And so back to our Fourier series motivation for this. So you can see this is kind of like Fourier series. Remember, in Fourier series you have x of t equal to summation k, ak e to the jk omega naught t. So here we also have this e to the j omega t. So we are also like summing over those complex exponential, right? So you see only sitting from the t is this e to the j omega t. So it's like you are summing over those e to the j omega t, but now omega is not restricted to k omega naught. Omega is a continuous variable that from minus infinity to plus infinity. And also because it's a continuous variable, you cannot really sum over them because there are too many of them. So instead we are taking an integral. That's kind of the idea. And once again, there is this weird 1 over 2 pi here. But that's just some normalization we need to take. Okay, so that's a quick review of what we've done so far. And I guess, maybe before I ask you a question, then we also finished a little bit. So this is kind of what we already done, but let's see this again. And we see that now we have those small x and big X relations. And once again, we can see those ak as the samples on big X of t. Okay, so let's do the derivation that we kind of see many times. So now we still have this weird x of t and the x tilde of t being like x of t copy and paste become periodic, and we want to see what are the ak of those x tilde of t. So maybe let's try to scroll back to x of t and x tilde of t. Okay, here. So x of t is like this, and x tilde of t is like this. It's a periodic function. Looks like the a of t in one period, but it keeps repeating itself. So we now ask that if we have this Fourier transform big X of x of t, what's the AK of x tilde of t? And we are going to see is the samples of big X of t like like we expect. Okay, so anyway, so the assume x of t has some support between s and s plus big T, and then we can calculate the AK by applying the Fourier series formula, the analysis for equation on Fourier series on x tilde of t, because x tilde of t is periodic. And so this is integration over one period thing, integration over one period times this minus complex exponential. And then we do the trick that we have seen before. So integration over one period of x tilde is equal to integration over one period x of t, because they are just the same in one period. And because you are only, but for x of t, everything outside of one period is 0, so you can change the integration from just one period to minus infinity to plus infinity. So AK equal to this minus infinity to plus infinity x of t e to the minus jk omega t. And if you compare this to our big X of t, yeah, you compare this to our definition of big X of t, this part is just big X of t, so it's just big X of t divided by 1 over t, and with 0 omega peaking with k omega naught. So yeah, so we've seen this similar calculation I think twice, but we see this third time. Okay, any question on our derivation of Fourier transform? And anyway, I think the most important thing is now we need to memorize those two equations. So remember that big X of j omega equal to integration minus infinity to plus infinity x of t to the minus j omega t dt, and small x of t equal to 1 over 2 pi minus infinity to plus infinity x of j omega, big X of j omega e to the j omega t d omega. Okay. Okay. Let you see this once again. Here we have a reverse order, but that's the same. Okay, so here is something a little confusing, and so some of this is you don't need to remember, but just want to say there are different conventions to push this 2 pi around. Okay, so depends on different books, different course, you will see that like someone like some of the people like to split this 1 over 2 pi evenly between your Fourier transform and the inverse Fourier transform. So that looks very symmetric. You have 1 over square root pi on both of them. Or sometimes you can not even see any of them in the front. You can change your normalization or the unit on your frequency. So instead of omega, you have like 2 pi f here, 2 pi f here. Then you won't have 2 pi. But yeah. Yeah. So this is kind of a reason that in our exam we always provide the equation here, because you might get confused with other notation. But but in our course we'll stick with our convention here. So it's 1 over 2 pi when you compute x of t. Okay. And okay, so that's the derivation of Fourier transform. And now we go to talk about the convergence of Fourier transform. And so this part let's go pretty quickly, because this is just very similar to what we have done for Fourier series. And we will now regress in Fourier series. We will also now regress in Fourier transform. So so yeah, so the issues are very similar, although there are some extra issues. So big X of t, so we have those Fourier transform pair, right? So you can calculate. So I think our signal will start with x of t, so we can calculate big X of j omega by this equation. So I believe this is called 4.9. And then you can calculate the x of t back from your big X of j omega by doing this integration. This is 4.8. Okay, so there are issues. So this cannot. Sometimes these big X of J omega just don't converge, and sometimes even if this big X of J omega converge, when you calculate back to X of T, it's not the same function. Okay, and anyway, so let's try to uh, parameterize how much error we have. So let's assume we have start with some X of T, then we calculate big X of J omega from here. Then we calculate back some x hat of t from this equation, and okay, so it's like this. And want to see what's the error we got. This e of t, that's your x hat of t minus x of t. And we think this should be 0, but sometimes it's not 0. And anyway, here we just claim very roughly that just like in the periodic case, if your x of t has finite energy, so like this, minus infinity plus infinity, absolute square integration is a finite value, then this energy of the error will also be 0. And this is a condition that we said as we think our series has good convergence. Okay, so where if you transform back and forth, then this energy of the error will become 0. So this actually has some trouble if you think a little more, because now we are not a periodic function, so there are one more way things can blow up, because integration limits, you also get electron infinity here. So there's another way things can diverge, and if you think a little harder, these things troublesome, but let's pretend that we didn't see that, and so this is what's said in a book, so we just think this is true, and we won't go into too much detail about this. Okay. And okay, so let's ignore an issue here, and now let's go to the other thing that's very similar to discrete case. So, sorry, not discrete case, in periodic case. So we have the directional conditions. Okay? And not directional conditions are a bit better. But anyway, so the directional condition for Fourier transform is very similar to those in Fourier series. So you have those three conditions. So first, that your x need to be absolutely integrable, but now the integration range is minus infinity to plus infinity. And also you want to have finite number of maxima and minima in any finite interval. Now this is a little different, because previously this finite interval doesn't mean much, because you just have a finite number in a period. But now period is basically infinity, and so you can actually have infinite number of maxima and minima for your function, but just you need to have the rate being infinite. So in any finite interval, the number of maxima and minima is finite. Okay. And similarly for discontinuity. So in any finite interval, the number of discontinuity need to be finite. And also the amount of discontinuity is finite. Okay, and so those things to be pretty reasonable things you want to argue as for your function, instead of for absolute integrable, because actually if you're integrating over such a large range, a lot of things diverge. But anyway, I think most of the function we see will satisfy those three. And if those three are all satisfied, then we have a pretty good convergence guarantee. So it's the same thing we have for the periodic function. So we say that the x hat of t equal to x of t at any t except at discontinuity. And but there will also be the Gibbs phenomenon issue, but let's also ignore that. We have seen that. So this is as we say, at every t, then you can at every t, then as your okay. So now there is no k goes to infinity convergence. Now there is at every t, then when you push this integration interval from So you're thinking about you put the integration interval from like some minus b to plus b, and then put the b to infinity, then then your x hat will converge to your x of t. Okay. But anyway, so I guess at a high level, we can say if your function satisfies all those three differential conditions, then we think the Fourier transform works, and so you can transform to small x to big X, and transform back from big X to some x hat, and your x hat will basically send us your x of t. Okay. Question? Okay. If not, then let's see an example. Oh, we're pretty quick today. And anyway, okay, so here is the example of Fourier transform. So this is a very nice converging Fourier transform. And just as a quick check, so let's check out this satisfy all three differential conditions. So we have seen this function quite a bit of time. X of t is equal to this exponential decay e to the minus at, and it's cut off at t equals 0 by this u of t. Okay, and okay, oh here. Let's just quickly draw it. I've seen this many times, but so x of t is like this exponential decay with rate a, and the cutoff is 0. So it's 0 here, and it's decaying like this. Okay, and we just say a is a real number less than 0, so it's actually decaying. Okay, and okay, so it satisfies all three differential conditions because you integrate this, then you are integrating over decaying exponential, and they should converge. And there's the maximum and the minimum. Well, there's basically one maximum, and it's a straight line, but let's see. Straight line is a little weird, but let's say it's like one minimum here. And so it's like 1, 2 maximum and minimum. And for discontinuity, there is one discontinuity here, and that's okay. Okay, so this is a pretty nice function. You should have a Fourier transform. And indeed, we can calculate this big X of j omega, and we just do brute force integration. It will be this integration from minus infinity to plus infinity, your function times e to the minus j omega t. And but it's u, so instead of from minus infinity, you can just integration from 0. Now we're just integrating some exponential, and e to the minus at, because it will become 1 over minus a e to the minus at, and so standard calculation, then you get your big X of j omega equal to 1 over a plus j omega. And the infinity term becomes 0 because you have this negative at. And so it's actually important that your a is bigger than 0, otherwise the infinity term will blow up. Okay. And yeah, so this is your big X of j omega, and it's a complex function, so we kind of plot it in the polar coordinate. So we plot its absolute value and its angle, and you see that because it's like 1 over omega, so as omega goes to bigger and bigger, you get this 1 over omega decay. So this is the biggest when your omega equals 0, its absolute value, so like this. And also then it has some weird angle like this. Okay. So yeah, so we think this function has most frequency component around omega equals 0, and as frequency get higher and higher, they get smaller and smaller. Okay, question? So it's a pretty nice function. And okay, so we say that a needs to be bigger than 0 for that to converge. So, but there are a little more a that the integration we do also converge. So as long as the real part of a is bigger than 0, then the integration we do will converge, and this this Fourier transform makes sense. And you can also see that check with the Dirichlet condition, right? Because only when a is the real part of a is bigger than 0, you will have this absolutely integrable thing. So say if a is less than 0, then you get the exponential growth here. Then obviously you do absolute value integration will be infinity, and you won't satisfy your Dirichlet condition. And although it's not if only if, but we also can check it directly here that when a is bigger than 0, then your integration just doesn't converge, and yeah, so you don't get your Fourier transform. Okay, and so there is something you need to really be careful about, and we'll actually see more about this in later part of the course when we see Laplace transform. That's don't do that for now. Okay, so this is the first example of Fourier transform. You see that we break this totally not periodic function into some of many different complex exponential with this omega from -infinity to +infinity, and some of the omega concentration trait around 0. Okay, and okay, so the next function. Now we pick one of our favorite function, but it's very singular. That's our impulse function delta of t. So what if our function is just this unit impulse at 0? Then, well, we can do the integration. So big X over j omega with this -infinity to +infinity integration. Then because we have this shifting property of x delta of t, so integrating over delta of t times another function, we just pick a 0 value of this, right? So we just pick t of 0 here, and e to the -0 is just 1. Okay. So we found out that this very sharp peak delta of t, if you do Fourier transform, actually has every frequency with the same amplitude. Okay. So you think about the spectrum, it's actually a constant. So something very interesting. Yeah. So delta of t do Fourier transform and become 1 for every omega. Remember, this is a function of omega, but this is just a constant function. It's 1 everywhere. Okay. And this is something that you want to remember. We'll see like a generalization of this. So you can think a little about what happens if you have delta t minus t0. Yes. Very quickly, anyone want to answer what happens if we have delta t minus t0 here? Then what's the Fourier transform of delta t minus t0? Okay. Yeah. So that will be very similar. So you have delta t minus t0 here. Then you also do the shifting property. Then, as we say here, then it becomes y of t0 here, right? So y of t is e to the minus j omega t. So you just have e to the minus j omega t0 here. We'll see that more later. Okay. And anyway, let's see the next example for Fourier transform. So this is like our favorite function, or square wave function. And as we said, is kind of base something to do Fourier transform because it has this discontinuity here. It's a very sharp angle. And yeah, we are basically trying to approximate this function with sharp angle with a whole bunch of complex exponentials that are very smooth. But we think that it will work out with some Gibbs phenomena. And anyway, back to our calculation. So x of t is this circular function from -t1 to +t1, and we say its height is 1. And we can just brute force do the calculation. We do the integration to get our big X of j omega, and that will be an integration from -t1 to t1 with the value 1, so times this e to minus j omega. And you do the integration, you see this is, so you get the 1 over j omega from doing integration here. And then you have sine omega minus sine plus, yeah, anyway, so you have sine j omega minus j omega, and become this. Sorry, excuse me. So you have e to the j omega minus e to the minus j omega, and let's get you this sine omega t 1 here. Okay, and yeah, so you have the sine omega over omega function. And here we are being a little lazy. So you see this is sine 0 over 0 when omega equals 0. But here we just use continuity and say sine 0 over 0 it will become, so this sine something, sine omega over omega will just be 1. And if you have this sine omega t1 over omega, it will be t1 if you do the limit. And also you can just check if you take omega equals 0 here, so that's just 2t1. Yeah. And anyway, so we assume we can take the 0 over 0 here by just having t1 here. And so we don't write this in cases, so being a little sloppy. And anyway, you plot this sine omega over omega, then you look at this function. So you can see it's the sine function, but it's decaying with 1 over omega here. Okay. So your circular wave function, you do Fourier transform, it becomes this sine over sine function. And just as we said, because you are approximating something with discontinuity with very smooth function, we're trying to approximate this with a whole bunch of e to j omega. And so we also get Gibbs phenomena here. But so before the Gibbs phenomena, we say is when we chop off our summation of k at finite k. And here a similar thing is we chop off the integration at some finite omega. So when we do the reverse transform, remember we need to multiply this big X over j omega with e to the minus j omega, e to the plus j omega t, the integration omega from minus infinity to plus infinity. And so if we chop off the integration from some finite value minus big W to plus big W, then you will see the Gibbs phenomena here, so you will get some ripple of finite width height here. Okay. Finite height, but the width of the ripple will go to 0 as your big W go to infinity. Okay? Question? Okay. Not? Then, yeah. So something very interesting is you can do this in kind of reverse. We'll see a little bit more. So there is a symmetry between small x and big X. So now you think about if we have big X over j omega as the square wave function here. So it's 1 and between this minus big W to plus big W. And then what function will have Fourier transform to this. And then we can do similar thing. We can do the inverse Fourier transform calculation here. Right? So x of t, you do the similar calculation. It's also this will be the integration minus w to plus w e to the j omega t. And so the only difference is there is no minus sign here, but it's really the same thing. And also you have 1 over 2 pi. So with a little difference in constant, you see that you have x of t. So you start with this big X here, and then you do this inverse Fourier transform calculation. So you see your X is this sin t over t. Okay, so very similar. You see it's basically the same thing. So the big T1 here becomes this big W here, and also you have this 1 over 2 pi, so 2 become 1 over pi. So you see that the inverse Fourier transform of this square wave is this sine over sine function, and That also means the Fourier transform of the sine over sine function is the square wave function. Okay. So we learn the Fourier transform of HR function. So we learn that if your input x is its sine t over t, sorry, not sine over sine, so sine t over t, then its Fourier transform will be square wave function, because we know this. You can always do the reverse of inverse Fourier transform by doing the Fourier transform, because you can keep back and forth, and because those are both nice functions, it will be good. Okay. And okay, so maybe we can check a little bit that this is a good function. So it's a little hard. So if you do the integration, it will actually converge. It's a little hard, but you can check the minimum and the maximum. So minimum and the maximum, there are infinite number of minimum and the maximum, but they are spaced out with like a period like 1 over t1. So it's finitely many maximum and minimum, and there is no discontinuity. So this is a nice function that will have it satisfy the Dirichlet condition, and you should be able to go back and forth the Fourier transform, and it will become the same function. Okay. Any question here? So we find out that there is a very similar thing between Fourier transform and the inverse Fourier transform, because you are basically doing the same integral with a little different constant and some negative sign on your e to the j omega t. And that also allows us to find the Fourier transform of some different function by doing the inverse Fourier transform of easier function. Okay. And yeah. And also we can tune the parameter for this Fourier transform a little bit. And we see a general phenomenon here. So we see that if you change, so let's think about changing this w, so the width of this square wave here. And then we didn't quite say, but you can check the formula here. So this is sine big Wt over pi t here. So will be 0 when this Wt equal to integer multiple of pi, right? So because sine something equal to 0 when this is like k pi. So Wt equal to k pi, then t equal to k pi over w. Okay. So this point will be k pi over w. Except k equals 0, it's actually w over pi. But anyway, so this point will be pi over w, this will be minus pi over w, and this will be 2 pi over w, etc. 2 pi over w, 3 pi over w, etc. And what we want to say is you have bigger w, then you have smaller pi over w. Okay. So if it's wider on the frequency domain, it will be thinner on the time domain. And similarly, if it's thinner on the frequency domain, will be wider on the time domain. And this is actually a general phenomenon, as we'll see later, like in the stretching and squeezing of time and frequency for the Fourier transform property. And so if you squeeze your signal in the frequency domain, you will stretch out in the time domain proportionally. Okay, so that's interesting. And finally, let's make some notation. So we keep calling these sine t over t or sine omega over omega functions, and that's very annoying. So let's introduce a name for them. It's called sinc function. So I guess there is not too much we learned from doing this definition, but it's very convenient because we keep seeing this function because it's a Fourier transform square root function, and we kind of like square root function. And anyway, so we give this function a name is sinc function, and there is some notation, there is some convention here. So we define sinc theta as sine pi theta over pi theta. So there is a normalization here with a pi before theta and a pi before theta. So you have a different function, so say this, then you need to change things around, right? So like you have pi t here, but you have wt here. So this is not sin x of t, you need to like change your t a little bit, so this is actually sin pi t here, etc. But anyway, so this is a sinc function, it's very nice. And you plot the sinc function, so we have pi here, so all the 0 point, the roots of the function will be nicely at the integer. Because the integer you have sin k pi, and sin k pi is 0. Okay, and so we plot it here, and everything is normalized nicely. And also at theta equals 0, then it's basically pi theta over theta, so you have sinc 0 equal to 1, and sinc k will all be 0 when k not equal to 0. Okay, so it's normalized nicely. It's a sinc function here. Okay, and so then we can write our result in terms of sinc function, and here we do something else. So maybe I should also draw a picture here. And we also introduce another name for rectangular function. But I believe rectangular function we don't do that much. Anyway, let's draw the rectangular function. It's also normalized. So rectangular function will be, so we normalize to be, so height we like it to be 1. Okay, and so let's draw this like a square wave. So our rectangular function or square function is this. Oh, sorry. Okay, let's try to draw this nicely. Okay, so it's just a square wave from -1/2 to +1/2. 1/2 height. Okay. So yeah, so it's a square wave with width 1 and height 1. Okay, so it's 1 here and -1/2 +1/2, and we call it pi of t. Obviously, this t can be switched to other thing. It can become omega also. Anyway, so this is our square wave function. And we can write all our previous result as a different scale sinc function and a square wave function. So for example, I believe the starting point kind of here. So we can transform a square wave function become a sinc function, and that will be this equation. Although here we don't have the t1 here. But anyway, so that's like we choose the t1 as 1/2, then this is just the Fourier transform the square wave function, then it becomes the sinc function. But you need to renormalize things a little bit. So so we have this 2 sine omega t1 over omega, and you need to do a little change of variable, and you see that's actually sinc of omega over t1, omega t1 over pi, and 2t1, okay, etc. And yeah, and you pick t1 equal 1/2, so this is 1, and you are left with sine omega over 2 pi. And okay, and similarly, so if you do the other exercise, then you will have the, the other exercise, so you have the sinc function in time domain, then transform to this square function in frequency domain, etc. Okay. Okay, any question? So yeah, I guess the bottom line is if you Fourier transform of sinc function, it will become a square function, and you do Fourier transform of square function, it becomes sinc function. And actually, the time domain and the frequency domain can be interchanged. Okay. But there will be some normalization difference you need to be careful about. Okay, so 5 minutes. Well, 5 minutes, so let's stop here for now, and we'll start talking about periodic functions, Fourier transform. Okay, next class.写错了。 Okay, and I think it's about time we can get back started. Okay, so yeah, so we see some example of Fourier transform before is we see the sinc function transform to square wave function and the square wave function transform back to sinc function. Okay, so that's nice. And here we switch to another topic about the Fourier transform of a periodic signal. So the logic here is a little confusing, but it makes sense. So the idea here is that, so remember in chapter 3 we say a periodic signal, then we have Fourier series. And then we say, what about periodic signal? Then we got in chapter 4 and we get Fourier transform. But now we are greedy, so we say we have Fourier transform for every aperiodic function, and how about can we also write the periodic signals with Fourier transform? And we found out that we actually can. We just need to use uni impulse. Okay. So for the periodic signal, we have the Fourier series, but we can also represent the Fourier series some kind of Fourier transform. So we can, I guess, So you have Fourier series, but we can also write them as Fourier transform, just that the Fourier transform will not be like a linear combination of a whole bunch of uni-impulse functions. There will be a whole bunch of delta functions. And so the intuition very quickly is that if you have a whole bunch of delta functions, then you integrating over them, then you get some discrete value at the point of the delta functions. So when you integrating over those delta functions, you are basically summing over your Fourier series. So I guess that's a little hard to see. So let's see a more concrete example. So this is what we want to do on the Fourier transform periodic signal. And we see that we can do that with a whole bunch of delta functions. And let's start with a very easy example. So let's assume we have so we say the periodic signal for periodic signal is Fourier transform. So the spectrum x of j omega will be a whole bunch of delta function. So just think about what happened with our big X of j omega will just be one single delta function at omega equal to omega naught. Okay? And because of normalization, we also multiply by 2 pi. So this is impulse with area or height 2 pi at omega naught. So like if you draw this on the omega plane, it's just one. Oh, what happened? So you draw this on omega plane. Wait, huh? Oh, see. Sorry. We draw this on omega plane. It's just a single peak, single spike with this height 2 pi, and the omega 0. And okay, so this is our big X of j omega. And then we can do our inverse Fourier transform formula and calculate what the x of t correspond to this. And well, the formula is here, and this is the integration. So you are integrating over this delta function, and by the shifting property of the delta function, you will just pick out at omega equal to omega naught. So you swap this omega equal to omega naught, then you got e to the j omega naught t. And you see why we got 2 pi here, because the 2 pi will cancel with this 2 pi we had in our convention. Okay? So x naught, so your big X is this delta function at omega naught times 2 pi, and your x will be e to the j omega t. Okay? So here we prove this very nice, useful Fourier transform pair. So e to the j omega t is Fourier transform will be 2 pi delta omega minus omega naught. Okay? Question? So if you buy this, then we can easily construct the Fourier series here, right? So we got the Fourier transform of this complex exponential e to j omega naught t is this 2 pi times the delta function. And then, although we didn't say it, but it's very easy to check that Fourier transform also satisfies linearity. So if your x of j omega naught is not a linear combination of a whole bunch of the delta function with different coefficient ak here for obvious reason. So you have a whole bunch of this delta function placed at point k omega naught, and then we have k from minus infinity to plus infinity, and then we have this linear coefficient ak, and because Fourier transform actually have linear property, then your x over t will be the corresponding linear combination, right? So you have this on k ak, and you have a whole bunch of this e to the j omega naught. But now omega naught is actually k omega naught, so you have e to the jk omega naught t. Okay. And but you see that this is just a Fourier series representation for your periodic function, right? For your periodic function with period 2 pi over omega naught. Okay. So you see that if your big X is the summation of a whole bunch of delta function with equal spacing at k omega naught, then that's correspond to x. That has Fourier series coefficient ak. Okay. And yeah, so basically we have this Fourier pair. So these Fourier series expansions on ak equal jk omega naught t, it has Fourier transform sin k 2 pi ak delta omega minus omega. So here we have a little error, right? So it should be omega minus k omega naught. Minus k omega naught. Okay. So yeah, so we see that you have these equally spaced out delta functions as your Fourier spectrum. Then we can actually think that as the Fourier transform of Fourier series, or as a periodic function, because we say every periodic function can be written in this form. Okay, so that's the idea. And let's see an example. So we have our very favorite periodic function, this square wave. So square wave with period t and with 2t1. And we've seen we've seen how to write this in Fourier series, and so it's sin ak to the jk omega naught t with this ak. That's kind of like sinc function, but it's discrete, so a little weird. Anyway, so we don't quite write this as sinc yet. So this is sin k over pi k thing. And then we can do the correspondence we just have. So x over t equal to this Fourier series. Then we can basically immediately write down the big X over t, right? Big X over j omega. Because big X over j omega is just this form. So some 2 pi ak delta omega minus k naught. So and we have ak here. So write down the big X over j omega here. Okay. So it's a whole bunch of delta function at k omega naught, and also we know this ak looks like a sinc function, so like this. So it's also, so this is the first time we see this kind of sampling property. So so we see that this big X of j omega here for this periodic function samples from this envelope, like think like envelope here. And but it's a little different, but it's actually delta function. So those are go to infinity, but with the area being this ak. Okay, 2 pi ak. Okay. Okay. So any question? So well, how we think the Fourier transform of any periodic function is just a whole bunch of unit impulse or delta function placed at a point that's k omega naught. So for every k, then the height is 2 pi ak. Okay. Yeah. So yeah, we can also write the Fourier transform of periodic functions, and so I guess we can think a little about this. So how should I say? Sorry. So if you think a little more about what we done in previous class, so this is not converging, but we are still okay with this because now x over t is periodic. So obviously you integrate it's from minus infinity to plus infinity, either its absolute value or its energy is all going to converge. But so you see that we are pretty lenient on our convergence of Fourier series. So even though this doesn't satisfy the Dirichlet condition for the convergence for Fourier transform, So although this doesn't satisfy the differentiation as the function from minus infinity to plus infinity, or it doesn't have finite energy, we still think we can write its Fourier transform like with this very singular function. So we see that because it doesn't satisfy the differential conjugation, so now the Fourier transform is a bit funny. We got the infinity everywhere. It's a whole bunch of delta function, but yeah, we are pretty easygoing on what we allow to have a Fourier transform. So even delta function, we think they are valid things. Okay. And okay, so that's on digression. Anyway, let's see even easier example. So x of t is sine omega t, sine omega naught t. So obviously this is a periodic function, it's a sine, so it keeps going minus infinity to plus infinity. And well, its Fourier series coefficient is pretty easy. We can do this without any integration, as we see in previous chapter. You just do our inverse Euler, so sine is exponential minus another exponent minus a negative exponential. So and easy to see that a1 is 1 over 2j and a minus 1 is minus 1 over 2j. So you plot its spectrum, then it has this delta function with pi over j and this omega naught and the minus pi over j and the minus omega naught. Yeah, similarly for cosine, so cosine is the complex exponential plus another complex exponential, and you plot its spectrum is here, so this is pi and the pi here, and omega naught and minus omega naught. Any question? Not. Okay, then let's see a very interesting function. So it's a periodic function that also have a whole bunch of delta function. Okay, so this is called the impulse train. So it's equally spaced out delta function with the same height. Okay. So let's think if our x of t is this periodic function that are also delta function, so it's just here we just have delta of t minus kt. So it's delta function with area 1 and at every big T. Okay, so obviously it's a periodic function because it repeats itself every big T. Okay. And so what are the Fourier transform of this function? So what do we do? So first we think about how to run the Fourier series coefficient for this thing. So Fourier series coefficient, so we take out one period, so like minus over t over 2 plus t over 2. Then we use the analysis formula. So we do this delta function times minus complex exponential integration and over 1t. And so this delta function will just pick out the t, small t equal to 0, and e to the 0 is equal to 1. So integration is just 1 here, then it becomes 1 over t. So we found out that the AK for this thing is a constant for every k. Remember, this is actually a function for k. But when you do the integration, this doesn't depend on k. So there's a constant function 1 over t. And then we, okay. So every AK is 1 over t. And then we substitute back to our Fourier transform big X of j omega. Then that should become, so your summation, then ak 2 pi times ak, and but 2 pi times ak is just a constant, so that's 2 pi over big T, and you have the spacing with omega naught, right? So omega naught will be 2 pi over big T. Okay. So omega minus k omega naught. So this is your spectrum. And you see that this is actually basically the same thing. So you do this impulse train, then Fourier transform become another impulse train. And so it's an impulse train with height 2 pi over big T, and the spacing is 2 pi over big T. Okay. So this is a very interesting and sometimes and also useful Fourier transform pair to remember. So you have an impulse train like this. Then you do Fourier transform, it becomes another impulse train. And also, just from this, you see that you have a spectrum being impulse train, and you do inverse Fourier transform. You also get an impulse train. So that's very nice. I guess one thing nice is those two things looks very similar. And also you have some property that you've seen many times. So you see the spacing here is t, big T, and spacing here is 1 over big T. So if you have a spacing larger here, then spacing will be smaller here. And that's the general formula phenomenon we have been seeing. Okay. Okay. Any question on this example? Yeah. And I believe this is the example. Yeah. Yeah. So this is all example over 2. So this has a lot of symmetry. So for the impulse train is periodic, and also it's a linear combination. So it's also a linear combination of delta function, and then we see Fourier transform is also periodic. So you see, because you have a equal z space of the delta here, so by the same logic, you will have a periodic big X, and you see this periodic period big T, 1 over big T. Okay. If no question, then we should have enough time. Okay, so let's go to just like the next chapter. Let's go to the property of the Fourier transform. So we have a whole bunch of property, and they are basically same as the Fourier series. But in chapter 3, we skip the even odd thing, and so we'll spend more time talking about what happens when your x of t is even or odd function. Okay, so yeah, property of Fourier transform. So once again, remember this is our Fourier transform formula. Can calculate big X from small x like this, and small x from big X like this, and you can do back and forth as many times as you want. There will be the same thing. You will always come back to the same thing, and so you have a pair between small x and big X. Okay, so first property, linearity. As we said, there is linearity, and we don't bother with the proof here. You can plug in whatever into those two formula, and you see that you have a function small x that's Fourier transform pair with big X, and a small y Fourier transform pair to big Y. Then you have a linear combination x plus by. It will be a Fourier transform pair to a big X plus b big Y. Okay? It's pretty easy to check. Say you plug x plus by to here, then you see you have a x plus by here, then you get a big X and a b big Y plus b big Y here. Okay, so it's very easy, and skip that. Then we have time shifting, and yeah. So what happens if you get a time shift on your small x? Small x becomes small x of t minus t0. Then we'll get e to the minus j omega t0 big X of j omega. And it's pretty straightforward. I think you can do either of these, but here we cannot do in reverse. So we try small x as big X and integration, and we substitute t by t minus t naught on both sides, and we see that is the Fourier transform of this big X times h e to the minus j omega t naught vector. And this is just similarly to what we had in Fourier series, but I believe in Fourier series we have minus omega is k omega naught here. Okay. But it's very similar. And anyway, so from the linearity and the time shift, then we can do a whole bunch of tricks to calculate our Fourier transform. So for example, we want to do a Fourier transform on these kind of funny block functions. So it's from 1 to 4. So from 1 to 2 is 1, from 2 to 3 is 1.5, and from 3 to 4 is 1. So we can break it up by linearity into two square root function because we already know how to do Fourier transform square root function. So it's a one square function from 2 to 3 and another plus another square function from 1 to 4. And then we do a time shift. Okay. So we think this function is actually a square root function. So square root function with is with 1. So we'll account for this part. And height 1/2. So 1/2 here. And another square root function that has this width 3 here, and height 1. Okay, so x1 plus x2, and also is tangent by, so those says center is t equals 0, but this is center t equals 2.5, so we're tangent 2.5 here. Okay. So this is a linear combination of those two square wave functions with scaling and tangent 2.5. And we know the Fourier transform of those square wave function is these two sinc function. Okay. And they have two different widths, so you have a little difference in a sinc function here, in a coefficient of a sinc function here. And yeah, so you just do all the formula. So x1 has Fourier transform this thing, and x2 has Fourier transform this thing. And the total thing has a Fourier transform being the linear combination of those two, with the 1/2 here, so these two disappear. Then, as we said, we tangent, so both of them should by 2.5, so that's easy. So they all have this HR factor e to a j omega dot t0 here, j omega t0 here. So j omega and t0 is 2.5, that's 5/2. Yeah. So this is the Fourier transform of everything. Okay. And yeah, so obviously you are going to see this in homework and public exams. Okay. And as we said, about okay. We're going to talk about the even odd and the conjugation a little more here. So first, let's start with conjugation. Conjugation is just like in Fourier series. And okay, so we could prove here, but let's not spend too much time on detail. So anyway, we first check what happens if we take a conjugation on our on our signal in time domain. And we see that we get a conjugation on our signal. Then we get a conjugation on our Fourier transform, and also frequency reverse in our Fourier transform. And this can be just done by brute force calculation. So so we are doing this in a bit funny way. But we are doing a conjugation of this big S of j omega, and we see that we take a conjugation and inverse both, and you do some change of variable, etc. Then you see that's the Fourier transform of your x conjugation. And anyway, so this is very similar to what we had before. We have that if, so for Fourier series, we have that if xt become x star of t, then your AK become A star of minus K, right? So you have this star and the minus. So you have the minus K here, you have minus omega. Okay, and just like before, we have this. Then you can easily derive from here that if x of t is real, then your x of j omega should equal to x star of minus j omega, and then yeah. And then we can also swap the minus sign around, then we have x of minus j omega equals to x star of j omega. Okay, so this equals to this, so x star of j omega equals to x of minus j omega. Okay, this is what happens when your x of t is real. And now we can think things a little. Yeah, because now we think big X of j omega as a function, so we analyze it a little more than our AK. So first is yeah, so now we analyze a whole bunch of things for real function. The Fourier transform real function. So first is we split this big X into real part and imaginary part. So this you can always do for any x of j omega, just because it's a complex function. So there is a real part of big X and the imaginary part of imaginary part of big X. And now we think what happens if you have small x is real, then big X or minus j omega equal to the complex conjugate of j omega. And you combine this with this, then you see that yeah. Yeah, so if you take the negative, then both of these get negative, but you get a conjugate, then so you see the conjugate of x to omega is also still the real part of x to omega, but it will be a minus j over the imaginary part. Okay, so yeah, so you put those on both sides into this equation, then you will see that when you how should I say? Yeah, when you conjugate, then the real part doesn't change. So the real part of x j omega is equal to the real part of x minus j omega. And okay, so we are actually missing a little thing, but it's obvious. And this will, you can easily convince yourself that this is real, and this frequency inversion actually commute, and this is equal to minus of sorry sorry, a little confused here. And real of x minus j omega. Okay, that's okay. Sorry. Yeah. So this should work here. And anyway. Okay. Yeah. Sorry. So anyway, so this means that this real part of x j omega is an even function, because will take omega to negative j omega. You take omega to negative omega, and this function stays the same. So you see that the real part of x j omega will be an even function. And similarly, so you take the imaginary part, but because you take a complex conjugate here, you get negative side. So you see the imaginary part of x of j omega equal to negative of the imaginary part of x of minus j omega. So this is the other function. Okay. Sorry, takes a little too long. So anyway, so x is a real function, then you see that big X is the real part is even, and its imaginary part is odd. And similarly, we can do a similar thing in polar form. So we can also write big X in as the known and the angle. And then we do this x minus j omega equal to x star of j omega. Then you take x minus j omega, then it's so you have everything equal to minus j omega here. And the other side, you take the polar form of x star of j omega. And well, the polar form of x star j omega, the known will be the same. But when you do conjugation, you will get a negative sign on your angle. And you equate those two signs, and you see the known doesn't change when you change from omega to minus j omega. So the magnitude is an even function, and for the angle you get an extra negative sign here. So the phase is the other function. Okay. Something interesting. Okay. And then let's do something that we haven't seen before. So what happens if our x is an even function? And so this is actually even simpler than the conjugation. So the fact is that basically x of t is even, and big X of j omega will also be even. And this is actually if and only if, and also for odd. But anyway, let's see one part of the proof. So the small part. So x of t is even, then we show that big X is even. And so we first start with this Fourier transform equation here, then we swap omega to negative omega. So we have big X of minus j omega equal to this integration, so things are all the same, but omega to negative j omega, so we don't have a negative sign here. And then we just do a change of variable and use the fact that your x is even. So first we do change of variable, so we want to get back this negative sign on exponential. So change t to negative tau, so or every t to negative tau. And then we see that then we use the x is an even function, so x of tau equals to x of minus tau. Okay, so x of minus j omega equals this integration. Then we skip one step, so you can change this integration of tau back to t, because tau is just a dummy variable. And you see that, so you compare this thing to this thing, then you see that this is just x of j omega. So we prove that x of minus j omega equals to x of j omega, and that means x of j omega is an even function. And similarly, okay, so you can prove any similar thing. So say if xt of is odd, then you will get a extra negative sign when you do this step. So you will see your big X of j omega is also odd. And you can do everything in the inverse Fourier transform. Then you see that if x of j omega is even, then x of t is even, etc. Okay. Okay, so that's very nice. Question? If not. And okay, so then now we can combine this with the real, and we don't actually talk about imaginary, but it's very similar. So let's combine this with this even odd with the real imaginary thing. So let's say if we have the real and the even x of t, then we will have the starting from x is real, we have x minus j omega equals a star of j omega. And then just from this even analysis we have here, we also have that if it's even, x of minus j omega also equal to x of j omega. So in the end we have this thing, so x star of j omega equal to x minus j omega from real, and x minus j omega equal to x j omega from even. And so we see that big X is even, and it's also real, right? Because big X equal to big X dot. Okay. And so we arrive at the conclusion that if your small x is real and even, then your big X of j omega is also real and even. So that's a pretty nice property. And you can do similar thing, right? So if this is, so you can do similar thing for all the four combination here. So for example, okay, so this is a little hard. So now to get this, confuse yourself. So if it's real and odd, let's see. So if it's real and odd, so this part is still the same. So x star of j omega is still x minus j omega. But it's odd, so this x minus j omega is minus x of j omega. So that's right. So here. So if it's odd, okay, then x star j omega equal to x minus j omega equal to minus x j omega. So what does this tell us? So obviously it's still odd, because the even and odd are just even leaf, but the x star will be minus x. Okay, so if it's odd, then it's actually odd and imaginary. So if a small x is real and odd, then big X will be imaginary and odd. And let's skip ahead a little bit. And so you can get the O4 property here, O4 combination here. So first, as we say, even if x is even, then big X is even. X is odd, then big X is odd. And x is real, then we have this. Okay, so it is knowingly different notation. So, but then we have the x dot equal to x of minus j omega. And you can easily similarly to derive that if x is imaginary, then you have this x star equal to minus x of minus j omega. Okay, you have a different thing. And then you can do the combination of all four of them. And for example, we have seen that if x is real, even, then big X is also real and even, and x is real odd, then big X will be imaginary and odd. So you see that odd will also always flip the imaginary and and the real thing. But anyway, and if x is imaginary and even, then big X is also imaginary and even. Let's see, we do this here quickly. Control P. Yeah, for example, this thing will be so x minus x dot of j omega will equal to x of minus j omega. This is from imaginary, right? We are just swapping things around because we want this x of minus j omega. And if it's even, this is also equal to x of j omega. And so once again it's even, but if you compare those two, then you see that when you get a star you get a negative sign, so this is also imaginary. Okay. So anyway, we have all those four conditions. Okay, and yeah, and this slide is okay. So this slide we have a little example here. So we'll see that yeah. So this slide we see that in example 4.1 we have this x equal to this is the exponential decay e minus at with u, and if your a is real, then our x is real, and then our big X of j omega is actually complex 1 over a plus j omega. But we see that we take inverse on omega, then it becomes 1 over a minus j omega, and it's a complex conjugation. Yeah, it's a complex conjugation of our x of j omega. Okay, so yeah, so this thing checks out for this example of being real. Okay, question. Oh, well, a little faster. Let's see. Okay. And anyway, and there is a little more correspondence to this real and real function and real and even odd thing. So if your x is real, then there's a correspondence between the even and the odd part of x and the real and imaginary part of big X, because so let's see this slowly. So we can break x. So for any x, we can break it into the even part and other part, as we see in the chapter 1. So x you can break into even part and other part, and by linearity, you do Fourier transform and become even part and other part. Okay. And just from our derivation, the even part is obviously even and the other part is obviously odd. So and from just this table, so there's two lines here. So the Fourier transform of even part will also be even, and the Fourier transform of the odd part will also be odd. Okay. Oh, sorry. So this Fourier transform will be even, and this you do Fourier transform will be odd. And then now we back to using our real function thing. So remember when we talk about real function, we say real function will do Fourier transform, and if we break this into the real part and then the imaginary part, and the real part will be even and the imaginary part will be odd, right? So yeah, so the real part will be even and the imaginary part will be odd, and but also this is even and this is odd, and actually and it's very easy to show that for any function, the even and odd decomposition is unique. So you have one way to break into even and odd part, and another way to break into even and odd part. Then that even part just should equal to the even part, and odd part need to equal to odd part. So we see that this Fourier transform of the real part, this should just the Fourier transform of the even part, it must be equal to, oh, what happened? Sorry. So yeah, so where do I set? Okay. And so this equal to big X, and that's right here. So this is equal to big X and equal to real big X, and plus J imaginary of big X. And we say this is real, this is odd, and sorry, this is even, this is odd, and this is even, this is odd. So these two must equal to each other, and these two must equal to each other. Okay. Yeah. So that's a very nice thing, and yeah. So Fourier transform of the even part is the real part, and the Fourier transform of the imaginary part is the Fourier transform of the odd part is the imaginary part, and yeah. So we get those nice correspondence. The even part of X correspond to the real part of the Fourier transform, and the odd part of X, if we do Fourier transform, it becomes the imaginary part of the big X. And but you need to remember that this only happen when we have real function, okay? Because this being even and odd only happen when X is the real function. But for real function, we have this nice characterization. Let's see. We are a little ahead of time. Yeah. So I guess, yeah. It's not like you cannot solve questions if you don't remember this, but those are always good for us challenge check, and also will simplify some questions when you yeah, sometimes you can use those real imaginary even odd analysis to make solving question easier. Okay, let's see if 10 minutes maybe you can push a little more. Hello. Let's see. Or should we start next time? Differentiation. Maybe we can push this. Maybe we can push this example. Okay, so let's see an example of how to use the even odd transform. Okay, so so we consider the Fourier transform of this function, which we didn't talk about. So, but anyway, it's a transform is a function of two-side exponential decay. So e to the minus a absolute value of t. So for t both go to plus or negative infinity, this will give you an exponential decay. So function look like this with some a bigger than 0. So exponential decay and the exponential decay. Okay, and so if you look at the book, you will have some brute force. You can do some brute force integration to get this Fourier transform. But now we try to get this Fourier transform smarter. So we use example 4.1 because we see this two-sided exponential decay looks like one of each side looks like the exponential decay we had before, and what if we just flip it and add it together, then we'll get a two-sided exponential decay. Okay, so so let's see the one-sided exponential decay. This we did solve example 4.1 today. So this one-sided exponential decay. So if we cut off this at t equals 0, then we have seen that the corresponding Fourier transform is this 1 over a plus j omega. Okay, and now we think we can try to get back. So this one-sided exponential decay we call x bar. So we try to piece together x bar to x of t, and we can do it by by having x of t equal to this e to the minus a absolute value t. So the right side exponential decay is just e to the minus a t ut, and then we also have the left side exponential decay, and that's for t less than 0, that's e to the at. Right, t less than 0, then this become negative t, and so become e to the at. And you cut off at t equals 0 with u to minus t. Okay. So yeah, so we can think of this as the right side and the left side, but we see the right side and the left side has symmetry, so yeah, so we can write this as the average of the right side and the left side, and divided by 2, so we multiply by another 2. And but you see the right side and the left side has symmetry because this is just this function with t to negative t, right? So you take a t to negative t, then you get a negative t here, negative t here. So this is just taking the even part of our so this symmetrization. So this you have the x of t plus a x bar of t plus x bar of negative t minus 2. This is taking the even part of our exponential decay function, one-sided exponential decay function. Okay. So yeah, so our this two-sided function is the even part of this one-sided function, and it's also real. So then we can do the analysis we had before. So we want to take the Fourier transform of the even part of this one-sided exponential decay, and from just we said before, so here, so from what we just said before, this even part is Fourier transform will correspond to the real part of the Fourier transform. Okay. And yeah, then you can just take the real part. And okay, so but we need to times, so the final Fourier transform we want to take, so the Fourier transform of the two-sided function will be this 2 we have here, then the real part of this 1 over j omega we have before, and then you calculate the real part of this. So hopefully you still remember your complex course. Then yeah, you take the real part is a over a squared plus omega squared. Okay. And yeah. So this will be the same as if you just do the brute force integration over 2 parts. Yeah. Very little time, so maybe I can do a quick review. Okay, the quick example of how to take the real part. So if you take the real part of 1 over complex number, you do so 1 over a plus j omega. What you do is you want to make the denominator, well, the sign under here, you want to make it real, so you multiply with a minus j omega and a minus j omega, and so that's equal to a squared plus omega squared and a minus j omega. And then you can take a real part because this is real, and you just take the real part of the upper part, and so you take a real, then that's a over x squared plus omega squared. Okay. And yeah, so 2 minutes, so I guess we can stop now. And next time we'll talk about differentiation and other stuff. So differentiation is annoying because you'll get delta function, etc. Yeah, we'll talk about it next time. Okay, question? Otherwise, yeah, let's stop.所以昨天如果拜托第三章我们都做过了，上个礼拜第三章做完，第4章我们就可以来出 property 这些。